examples. So here we'll solve this 4 examples, and for all these 4 examples there will be one solution. So we don't have to write 4 different deterministic PDA for all these 4 different problems, but we can use the same solution for all these 4 problems, only we'll change the accepting state. So in case of the first one, x belongs to a comma b star, number of a in x is greater than number of b in x. So we have qa as the accepting state. If number of a in x is less than number of b in x, then we'll declare qb as the accepting state. If both are equal, definitely it will accept null as well. So q0 will be the accepting state. If number of a in x is not equal to number of b in x, so definitely qa and qb will be the accepting states. So now let us see that how we can solve this. So let us consider ABB. So definitely in which QB will be the accepting state. We will match A and B. It will cancel out. We have one extra B. So that extra B indicates we are in the QB state at the end. So it is accepted. Similarly, BAA. A and B are matched. We have A extra. So we'll stay in the QA state and it will be accepted if number of A's are more than number of B's. Similarly, we have AB AAA. So A and B will cancel out. Again, we have QA as the accepting state. BBA, so definitely QB will be left. So it will be the accepting state. Similarly, if you take the last one, BAA, AB. So BA will cancel out. AB will cancel out. So we'll get Q0 as the accepting state. So now to write the solution, we'll have this kind of set of rules. Q0, A, Z0. So now we want to keep a track that do we have any extra A. So when you get first A, we consider that we have one extra A as compared to B. When we consider this Q0, A, Z0, so Q0 initially we don't have extra A or extra B. So when we get the first A, we'll go to a state QA, so that QA represents that we have one extra A as compared to B, and QAZ0. So here you can see the difference. Why we are not pushing A on the stack? Because that A is inside the QA state. That QA indicates that we have extra A. That QA indicates that we have one extra A. Now QAAZ0. So now this time we'll push A on the stack. We have a QAAZ0. So when we are in a state QA and configuration on the stack is AZ0, that means we have total 2A extra as compared to B. One is in QA state, another is on the top of the stack. Now when the third A encounters QA, A and A, because that is also a valid configuration. First time when you get the A, it will change to state QA, so no change in the stack. It will be Z0. When you get the second A, it will change the top of the stack by pushing A on the stack. So we require one more rule, which is a recursive rule, QAAA, because first and second rules are not recursive. First rule is not recursive because we are changing the state from Q0 to QA. The second rule, QAAZ0, it is also not a recursive rule because at that time Z0 is on the top of the stack. So we need one recursive rule which can handle any number of A's. So QAAA. So this QAAA will give us QA and AA. We are pushing one more A on the stack. It is a recursive push rule. It is a push rule with recursion. We can apply any number of times. Now similarly we have QABA. So now QA is your current state, B is in the input, A is on the top of the stack. So first this A will match with B in the input and it will cancel out. So it is a recursive rule, QABA. So our state is still QA. The reason is that we have cancelled B and A. We have cancelled B and A. So we don't know what is below the top of the stack in the rules. When we solve the exact example, we know what is below the top of the stack. But in the rules, we only know what is the top of the stack, and it is cancelled by input B. It is QA null. And we can apply this rule any number of times. Now, we need this special rule, rule number 5, which is very important. QA B Z0. B is in the input, Z0 is on the top of the stack, and our state is QA. So this time it tells that we have used all the A's from the stack. We have used all the A's from the stack, but still we have one A is left with us. It is in QA state. So I can utilize that A which is with QA state. So the A which is in QA state will be which is compared with B, and it will be cancelled out. So we'll get a state Q0Z0. So when there are equal A and B, you will get this state Q0Z0. You will get the state as Q0Z0. Now whatever 5 rules we have written, that is for input A. And we have one pop rule, which is also for removing the A from the stack. So now exactly similar to first 5 rules, we require another rules. So that is rule number 6. If the first input symbol is B, from the Q0 state. So we'll go to QB. We'll consider a QB state having one B with it, and Z0 is still as it is on the top of the stack. So it is not a recursive rule. Now we need one more rule, QB BZ0. When the state is QB, we already have one extra B, and we are getting another B from the input, BB, like BB. So BB, at that time, Z0 is also there on the top of the stack. So we have to push B on the stack. So rule 7 is same as rule 2. You can match rule 2 with rule 7, right? Similarly, rule 8 is if we have third B, BBB as the input. If the input is BBB, what will happen? The first B will go to QB state. Second B will push it on the stack. Now when the third B encounters, at that time we will apply rule number 8, QB, BB. So again we'll push B on the stack, and it is a recursive push rule. We can apply it recursively for any number of B's. In the input and top of the stack is B. So now we need a pop rule also. We have QB, A, B. It is QB, AB. So it will cancel out A and B. So we'll get QB null. It will get QB null. So we require one more rule here, similar to rule number 5. That is QB A Z0. We also need a rule QB A Z0. That is rule number 10. Right? We also need a rule QB A Z0, which is similar to 5. So it will cancel out B, which is in QB state, with A on the top of the stack. Last A, which is on the top of the stack, which is in the input. Right? Because top of the stack is Z0 now. So the last A in the input will match with QB, and B and A will cancel out. So again we'll get the state Q0 Z0. So I think now you are getting this, right? That is, so first 5 rules and 6 to 10 rules, they are identical. Only difference is A and B. Only difference is A and B. So now if we trace these rules, if we apply these rules on any example, it will be like this. Let us see Q0, A, B, B, A, and Z0. Now all these are deterministic PDA, so we don't have multiple branches. We don't have a fork system call required here to try multiple alternatives. And suppose we are tracing for this language, X belongs to AB star, number of A in X is equal to number of B in X. We want to check equality of A and B. So that time our accepting state will be Q0. So if we are getting Q0 as the final state, then it is a valid string with a condition that we have used the entire input. So now here Q0 A and Z0. So what we'll do, we'll shift from Q0 to QA state, QA as per rule number 1, then BBA Z0. Now QA BZ0. So right now we don't have any A on the stack. So we have to utilize the B, which is with a QA state. So we'll apply rule number 5. We'll apply rule number 5 and we'll get Q0, BA and Z0. It is Q0, BA, Z0. Now again it is Q0, B, Z0. So we'll apply rule number 6. We'll go to QB state because it is the first B right now, which is more than A. So QB, A is the input and Z0 will be the top of the stack. Now we have A in the input. We don't have A on the top of the stack. We don't have B on the top of the stack also. So now we have to utilize the B, which is with a QB state. So that will utilize as per rule number 10, QB A Z0. So we'll get Q0 null Z0. So now Q0 is the accepting state for the language. Number of A in X is equal to number of B in X. And we have consumed the full input because it is null. So it is accepted. Right? So here you can see all these rules which we have discussed. Okay, now let us consider this language. We can see we are using the same push down automata rules. Right? We are using the same push down automata rules. So here it is, number of A in X is greater than number of B in X. So definitely at this point, our accepting state will be a QA state. It will be a QA state. So now Q0, B, Z0. So definitely we'll go to QB state because we are getting the first B extra as compared to A. So QB, AA, BA, Z0. Now QB, A, Z0. So again B and A will cancel out. So QB will convert to Q0 as we don't have any extra B on the stack. So it is Q0, ABA, Z0. Now Q0 and A. So this is an extra A because current state is Q0. So it is QA, then BAZ0. It is BAZ0. Now QA and B. So this A and B. This A and B will cancel out. So QA will convert to again Q0 as we don't have any extra A on the stack. So Q0, A, Z0. Now Q0, A, Z0. So we'll consider QA state. Input is null now and Z0. So for this language, number of A in X greater than number of B in X. Our accepting state is QA and we have consumed the full input. So it is accepted. Any query up to this example? Yes? Any doubt in this? Yes, are you getting this? How we are using the same DPDA rules for all the 4 examples? Yes, if you have any query, you can ask. Or we can proceed further. So it is clear to only one student? Okay. Okay, so now let us take another example. So I hope you can understand the previous one and you can try for different strings. Okay, now we have one more example here. Our language is X, middle symbol C, and Y. So X, length of X is equal to length of Y, and XY belongs to AB star. So definitely null is accepted. Null cannot be accepted because C is the middle symbol which is present. So null is not the accepting string. So Q0 will not be the accepting state. Okay, now you can see our input will be A, B, C, B, B, where length of X is 2 and length of Y is also 2. We can have A, B, C, B, A, where length of X is equal to length of Y. So here you can see that our significance is not whether the symbol is actually A or B. Our goal is not that we want to match the exact symbols. I do not want to match A with A, or I do not want to match B with B. Or in the POV operation, I do not want to cancel A and B, something like that. Right? In the previous example, we have seen that we are comparing A and B and we are cancelling it out. Here, in palindrome, we are matching A with A. But here, as per the question, we want to match only the length of X and length of Y. So now what we'll do to reduce the number of push down automata rules, what we'll do, we'll convert A and B into a one common symbol X. We'll convert A and B into a common symbol X. So A is converted to X. So our string will be double X, C, double X. You can see that our string will be double X, C, double X, where length of X is also 2 and length of Y is also 2. Right? You can take any symbols A and B also. Like we'll convert small a into a capital A, and we can convert small b also into a capital A. So now what will happen that everything in the input will be converted to a new symbol. So we don't have to check the different combinations of A and B, because our goal is we do not want to actually compare the characters. So now to achieve that goal, we are writing like this: Q0 A Z0. So when input is A, Q0 is your initial state. We'll push X on the stack. We'll push X on the stack. So now you can see that we don't know whether it was A or it is B. Similarly, you can see Q0 B Z0. If the first symbol is B, we'll convert that into also X, because we don't want to match at any place A and B. So Q0 X Z0. So now if the new A will encounter Q0 AX, at that time on the stack it will be capital X. On the stack it will be capital X. So Q0 AX, you are in a Q0 state. We have to do push operation until we will encounter the C. So we'll write Q0 double X on the stack. We'll write Q0 double X on the stack as A is converted to capital X. Q0 BX. Similarly, when B encounters in the input, X is on the top of the stack, we are getting Q0 double X. We are pushing that B by converting it into X on the stack. So what is the advantage? Can anyone tell that how we have reduced the number of rules? How we are able to reduce the rules? Yes, can anyone give the reason? That how this conversion into X will reduce the number of rules of deterministic push down automata? How it is beneficial? Yes, those who attended all the lectures, they can easily tell. That how this approach. Yes, so I got one answer from Kaushal. Good. Push A. Yes, Munaf has also given the correct answer. So push A on A and B reduced to only one step, right? So we are pushing A or B. So A and A, we don't require a separate rule. A and B, we don't require a separate rule. So A and A and B, the two rules will be converted into one. So Q0AA is converted into Q0AX, Q0. So AA, AB, BA, BB, that four rules will be converted into two. right? Q0AA, Q0AB, that is converted into one rule, Q0AX. So A and B is counted as one symbol. So we are reducing the number of rules. So once we are able to do this thing, when the C encounters, because it is the middle part, right? We are at the middle of the input, we can say we have to stop the push operation. So now we do not want to apply any of the previous rules. So we'll change the state from Q0 to Q1. Also, C is a special symbol. So we'll ignore the C. We'll not push it on the stack. So Q1 X, it will be as it is. X will be as it is on the stack. Now we are in a Q1 state. Now when we encounter A in the input and X is on the top of the stack, because it is a pop operation, Q1 state, we'll get Q1 null. Similarly, Q1BX. Q1BX. So again, B and X, it is a pop operation. So we'll get Q1 null. So when both are equal, our situation will be Q1 null Z0 and it is Q2 Z0. It is Q2 Z0. It is Q2 Z0. So I hope it is clear. Let us use these rules, right? So we are applying that rules here. So here we know the complete stack because we are using the rules to solve the example, to trace the string. So Q0 A Z0. So Q0 A is converted to X and it is pushed on the stack. So Q0 ACBB X Z0. Then again we have A. So Q0 AX, it is a push operation. So Q0 CBB double X Z0. Again A is converted to capital X and it is pushed on the stack. That's why in the definition of push down automata, you might have observed that input alphabet and the stack alphabet, tau, they are different. It is not necessary that whatever input symbol is there, we'll always put the same symbol on the stack, right? You might feel that why we are writing a stack alphabet as tau, and it is not same as the input alphabet sigma. But this example will clearly give the reason for that. That stack alphabet may be different from the input alphabet. Because here we have Z0 and X on the stack. No A and no B on the stack. So that's why sigma and tau are two different things. Okay, so now Q0C and X on the top of the stack. So definitely it is the end of the first part. So Q0 is converted to Q1. We have to do now power operation BB and double X Z0. Now Q1BX. It is Q1BX. So it is a power operation. B and X will cancel out. Again it is Q1B and XZ0. So B and X. So again it is a power operation. So it is Q1 null Z0. And it will give us Q2 Z0, which is accepted. Now if it is only C, then Q1 null Z0 will directly go to Q1 state. No push operation is required. And Q1 null Z0 will give us Q2 Z0. So it is accepted. Okay, now we have one more example. Q0 CBA Z0. So because it is C, we don't have to do the push operation. Directly we'll do the power operation. So Q1 state BA will ignore the C and Z0. Now Q1 BZ0, there is no such rule, Q1 BZ0. But we have a rule Q1 null Z0. We have a rule Q1 null Z0. So we'll get Q2 BA Z0. We'll get Q2 BA Z0. So this will not consider as a valid configuration because our state is an accepting state Q2, but we have not consumed the full input. Still, some input is left. So the machine will crash. So I hope this is clear. Yes, can you tell about this example now? Let us do a reverse thing. Can you identify the language for which this DPDA is constructed? Yes, can anyone recognize? Let us see that how many of you understood the thing. You take some input string and tell what is the purpose of this DPDA, which language it recognizes. You know very well when we are changing the state, right? Whether it is a push state, ignore state, or pop state. You can easily identify. Yes, can you identify? What is the purpose of this push down automata? It is also a deterministic PDA because there are no multiple rules, multiple alternatives for any moves, and also Q5 null Z0. So that Q5 and Z0 are not used with any another input alphabet. The combination of Q5 and Z0 is not used with any another input alphabet. Yes, if anyone can recognize. Yes, there are 95 people here around. So I think you can answer. Many people can answer. What is the purpose of this deterministic PDA? What language it will recognize? You can take some string, random string, and you can check. Are you able to reach up to Q6? Okay, so let me share another slide with you. I'm not going to tell the answer for this. You need to find out. So now I'm sharing another slide with you. I hope you are able to see the slides one more time. So now before we can start the new topic, some new terminologies we need to understand. So that is what we are discussing in this session. So let us define the term leftmost derivation and rightmost derivation of the string. A derivation in a context-free grammar is a leftmost derivation if at each step a production is applied to the leftmost variable occurrence in the current string. So always we have to select the leftmost non-terminal when you want to derive the string. From the starting symbol of the grammar, always our focus will be on the leftmost non-terminal. And once we can use the production rule on the leftmost non-terminal, we have to select the next leftmost non-terminal. So that is known as a leftmost derivation at each step. And similarly, in the rightmost derivation, it is reverse. So now let us see that we have this grammar. E gives t plus E or t. T gives f into t or f, and f gives a. So basically it is a grammar to generate simple expressions, right? It is a grammar to generate a simple expressions. Yes, are you able to see the second slide? Okay, there is some issue. I think now it will be visible. Yes. So here let us see the example that E gives t plus E or t. So basically it is a grammar to generate any arithmetic expression. You can see that we have a addition operation, we have a multiplication operation, and also you know that multiplication has higher priority as compared to addition. So as the priority of the operator increases, it is at a inner level in the grammar. This you have to keep always in your mind. As compared to plus, multiplication has higher priority. That's why it is at an inner level in the grammar. From E, if you want to derive the string a plus a into a, from E will replace with t plus E. So t will be the leftmost variable occurrence or non-terminal. So we have to apply the rule on it. So t is converted to f. So we'll get f plus E. Again, f is a leftmost non-terminal or a variable. So we have to apply the rule on it. So we are replacing f with a. So we have a plus E. It is a plus E. So now you can see the leftmost non-terminal because a is a terminal symbol. Plus is also a terminal symbol. We don't have any production rules for these symbols. So now we'll replace capital E with T. Then we'll replace T with F into T because our requirement is A into A. Our requirement is A into A. So now we'll replace T with F into T. So now F will be the leftmost non-terminal. F will become the leftmost non-terminal. So I have to replace F with A. So we'll get A plus A into T. We can apply only one step at a time. Then we have A plus A into last T is the leftmost non-terminal now. So we'll replace that T with F. So we'll get A plus A into A. So basically this top-down parsing or this push-down automata and TAFL, you will find we can say 25% of the syllables of compiler construction, right, is based on this. If you don't understand this TOEFL subject, right, then in the next semester, 7th semester, when you go for compiler construction, you cannot understand 25% of that subject. So it depends on all these things, leftmost derivation, push down automata, and everything. So you have to be very clear about all this grammar, regular grammars, and context-free grammars and everything, right? Otherwise, you will have definitely a problem in the compiler construction. Similar to that, if we write a rightmost derivation, then E is converted to T plus E. Now we are focusing on the rightmost non-terminal. So rightmost non-terminal is E. We'll write T plus T. Now for this rightmost non-terminal T, we'll write T plus F into T. Then we have the rightmost non-terminal is the last F, last T. We'll write T plus F into F. Then F is converted to A, so we'll get T plus F into A. Then the second symbol F is the rightmost non-terminal, so we'll write T plus A into A. For this T, we'll write F plus A into A. And finally, we'll get A plus A into A. It is the rightmost derivation. So basically, if G is a context-free grammar, then for every string X which belongs to a language, these three statements are equivalent. X has more than one derivation tree. X has more than one leftmost derivation. X has more than one rightmost derivation. Right? When you consider any string X, X has more than one derivation tree. That is possible. We can derive a string in more than one way. Or it is equivalent to X has more than one leftmost derivation. We can generate more than one leftmost derivation for the given string. Or we can generate more than one rightmost derivation for the given string. So it depends on the grammar. Some grammars can generate more than one leftmost derivation, while other grammars cannot generate a more than one leftmost derivation. So here we are considering E gives E plus E or E into E or A. So it is again a context-free grammar. E gives E plus E or E into E or A. So now for the string A plus A into A, we have different derivations possible, which are leftmost. You can see E gives E plus E. Now for the first E, we are writing A plus E because the first E is the leftmost non-terminal. So we are writing A plus E. Now for the E, we have A plus E into E. A plus E into E. So again the middle E is the leftmost non-terminal. So we are writing A plus A into E. We are getting A plus A into E. Then last we have A plus A into A. We have A plus A into A. So that is how we are getting one leftmost derivation, right? So if we take A equal to 3, you can see if you take A equal to 3, then as we want to calculate the tree, we want to evaluate the expression, then as per this tree, we have 3 into 3 will get 9. 9 plus 3 will get 12. We'll get 12, as you can see in the leftmost part, right? 3 into 3, right? When you evaluate this tree to get the value of the root. So 3 into 3 will get 9. 9 plus 3 will get 12. Now we have another leftmost derivation which is possible in this grammar for the same string A plus A into A. So keep in your mind that for one particular string, we have two different leftmost derivation. I am talking about only one string. For one particular string, we have two leftmost derivations. here. So you can see from E, we are writing E into E as a first rule. So leftmost non-terminal is E. So we'll write E plus E into E. So again, out of 3 E, the leftmost one will be considered. We'll write A plus E into E. Then we have A plus, middle E will be the leftmost non-terminal. So we'll write A plus A into E. And last we have A plus A into A. So you can see the derivation tree also here. So here, if we start from bottom to top to evaluate the expression, so 3 plus 3, this will be 6. 6 into 3, that is 18. So you will get the value as 18. So you can see same expression is there. The same expression is there, A plus A into A. Through same grammar, we are getting two different values, 12 and 18. So this kind of grammar are not useful in any programming language. The reason is how we will decide that what will be the output of your program. If this grammar is considered to develop a programming language which does a simple calculation like a calculator, then there will be an issue. You cannot identify that what will be the output of a given expression, because sometimes it will use the leftmost derivation like E gives E plus E at a first place, and sometimes it will take the leftmost derivation as E gives E into E at a first level. So the output will change. So what will happen that if you show your program to your staff, to your faculty member, it will give a different output. When you run the same program at your home, it will give the different output. So how you will tell that it is a correct program? And think about a bank. If bank is using this kind of grammar, then what will happen? Sometimes as per the second tree, you will get 18 as the value. And sometimes it will calculate as per the first derivation. So you will get 12. So how will decide that what will be the amount in your bank? So basically this kind of grammar where you have more than one leftmost derivation for any one string, it is of no use. It is of no use. So what we have to do, this kind of grammars which are known as ambiguous grammar. A context-free grammar G is ambiguous if for at least one x, we have to take any one x from the language, x has more than one derivation tree. That means more than one leftmost derivation. If you have more than one leftmost derivation, then it is an ambiguous grammar, and that grammar cannot be used practically. Is this clear definition of ambiguous grammar? That what is the problem with this ambiguous grammar? So you can see that we have taken the same expression, A plus A into A, and we have two different grammars. Here also we have the same expression, A plus A into A, but the grammar is different. So here in this grammar, E gives T plus E. It is not ambiguous grammar. It is not ambiguous grammar. So we are not facing any problem. But for the same expression, A plus A into A, if we use this grammar, E gives E plus E or E into E, then we are getting two different leftmost derivation tree. So this grammar is the ambiguous grammar. This grammar is the ambiguous grammar. So I hope the definition is clear. Any query in the definition? That if the grammar is ambiguous, it will give you more than one leftmost derivation tree for the one string, for at least one string x. So we cannot use that particular grammar. So the question will come that can we convert every ambiguous grammar into unambiguous? So the answer is no. Right? The answer is no. Right? That we cannot convert every ambiguous grammar into unambiguous grammar. So now here in this, right, we have because this example is same. Instead of E here in this, we have S plus S is used instead of E. E gives A, E gives E plus E, E gives E into E, and E gives within parenthesis E. So it is same as the previous one. So we are not discussing this again. Only one more alternative is given to handle a parenthesized expression, right? To handle parenthesized expression, one more alternative is given. So we are not discussing this same example, right? Okay, so now here you can see that we can generate more than one leftmost derivation because these grammars are ambiguous, and we cannot convert every ambiguous grammar into unambiguous grammar. So now here, let us see that how we can have two different leftmost derivation from the first one. So from S, we'll write SS. Now for the leftmost non-terminal, I will write A, S. Now for this S, I will write SS. We have A, S, and we have A. This is one option. Second option is I will replace S with SS. Again, I will replace the first S with SS. Now I will put one by one. S, replace S with A. You can see two different leftmost derivation. We have two different leftmost derivation for the same string A. In the first one, we are replacing the first non-terminal S with A immediately, while in the second alternative, we are replacing the first S with SS in the first step. So both are leftmost derivations. You can see that. Okay, so can you generate two leftmost derivations for the string A for the second grammar in the chat window like this? Yes, can you do that? Anyone? Yes, can you do this? Can you generate two leftmost derivation? The string I have given. Ideally, you should find out the string, but here it is already given. So can you generate two different leftmost derivations for the string A? For the second grammar? If it is clear, you can do that easily. Okay, so one option we have got. We are removing A with null. Okay, so it is BA, then we'll remove B. We'll get A. And for that A, we have small a, capital A, and A. That is one leftmost derivation. Now, second one. Now, where is B? You cannot remove the symbol from the middle position. You cannot remove the symbol from the middle position. Okay, here. No, you cannot remove the symbol from the last position. Yes, Kaushal, you cannot remove the symbol directly from the last position. We have to go for leftmost non-terminal always. You have to always process a leftmost non-terminal. Either you can remove it or you can convert into a terminal. So I think Nirav has written a correct answer. So S gives AABA. So you are replacing first A with small a, capital A. Then you will remove A, capital A. So you have A, B, A, right? Then you will have AA because you are removing B, and finally you remove A. So it is the another alternative, right? Another leftmost derivation. So I think it is clear now. Similarly, you can try for the other two grammars as well. Here we have one more example. So that the context-free grammar with productions given is ambiguous. So here we have one string B triple A, and we have two leftmost derivations, as you can see here. From S, we are getting BSS. Now B, I'm replacing the S with A. So we are getting BA, capital S. Now I'm replacing capital S with SA. So you can see we are always processing the leftmost non-terminal. All the symbols before the leftmost non-terminal must be terminals. All the symbols before the leftmost non-terminal must be terminal symbols. So BA, then AA, we are getting. Another alternative is S is replaced with BSS. So we are taking the leftmost non-terminal, the middle S. That middle S is replaced with SA, capital SA. So again, the leftmost non-terminal is the second S, S at the second position, right? The S at the second position will be the leftmost non-terminal. So we'll replace that with A. So we have BAA and capital S at last. So we have a B triple A. We have a B triple A. So we have two different leftmost derivations. Okay, now this is very interesting. This is a grammar for if-else statement. So if condition is there, any condition can be considered as an expression. So if condition is there, then we have a statement to execute. Or in the if-else statement, we have if condition is true, we have a set of statements, else we have another set of statements. And OS indicates any another statement, right? To terminate the process. So this grammar is known as a grammar for if-else statements of the programming language. So if condition is true, we have a set of statements. If we have a condition false, we'll go with the else part and we'll execute again a set of statements. So here, this problem is known as a dangling else grammar. This grammar is also a dangling else because you can see here in this derivation tree, you can see we are writing if, then opening parenthesis E, closing parenthesis S. So we are applying if statement only. In the if statement, we have a last S, and that last S, because if is a terminal, then opening parenthesis, then E is replaced with E1. E1 is any statement, any valid statement we can consider. So if opening parenthesis, then E, which is giving us E1, any valid statement, any expression 1 we can say. We have closing parenthesis and last S, the last S, which is replaced with if a condition statement else statement. So in the last S we have if else both. So you can see it will look like this. We are checking some if condition, and inside that if condition we have a entire if else construct. We have entire if else construct. You can see the bottom up approach here, right? The innermost is if else and the outermost is only if. The innermost is if else and the outermost is only if. If condition is true, that's fine. We'll execute it. Then from the last, after that, what we'll do? We have if else construct inside it. So now, if you write down all this, then you will get this statement. If opening parenthesis E1, closing parenthesis, because we are writing only terminals, then again if opening parenthesis E2, then we have closing parenthesis, we have some function call for our understanding purpose. So we are writing here f any dummy function. Then we have else, and we have another function call. So this is what we are getting the statement. So here, as per this tree, it is clear that else part is with inner if. As per this derivation tree, the else part is associated with the inner if. Now, because this grammar is an ambiguous grammar, same statement we can generate in a different way. You can see here that here if else is the outermost one, and inside the outer if we have only if statement. You can see the difference at the top right corner. If else is the outermost construct, and inside the if statement we have another if statement. So here else is associated with the outer if, right? Here else part is associated with the outer if, while in the previous case else part is associated with the inner if. So now if we draw the tree for this, because outer one is the if else construct, so we'll use that if opening parenthesis e closing parenthesis statement else statement. We are using that grammar, if else part. And then from that we have the inner if statement. So you can see that if opening parenthesis e is converted to e1, then closing parenthesis, then the first s that is converted into if opening parenthesis e2 closing parenthesis and s. We are writing only if statement from the s. So now when you write this in the form of an final expression, we will get this if within parenthesis e1, again if within parenthesis e2, function call for f, else function call for g. So this statement is same as the previous one. You can see no change. You can compare it both. So here from this second tree, what we can conclude, that else is associated with the outer if statement. So this is known as a dangling else, because the role of else in the grammar is not clear, because you have the same statement. When you write this statement in the program, if you are using ambiguous grammar like this, what will happen? The role of else is not clear, whether that else is linked with the outer if or the else is linked with the inner if statement. So this is an ambiguous grammar for if else statement. This is an ambiguous grammar for if else statement. So any another statement is what? You can consider this all function call and everything. Right? So basically this tells that if the grammar is ambiguous, we cannot use it because it will create a problem. Right? We cannot understand whether else is linked with if outer one or else is linked with the inner if. So this kind of ambiguous grammar are not useful in any programming language. And I think dangling else is clear. The role of else is dangling. It is not clear. It is linked with inner if. Also, it is linked with the outer if. So it is dangling. That's why it is known as a dangling else problem. So ambiguous grammar may create this kind of problems, and it is not used in any programming languages. And keep in your mind that you cannot convert every ambiguous grammar into unambiguous grammar. It is not possible. Every ambiguous grammar cannot be used, and every ambiguous grammar cannot be converted into unambiguous grammar. So that conversion of ambiguous grammar into unambiguous grammar is not in your syllabus of TOEFL. So we are not going into that detail, right? That you will learn in compiler construction or maybe in an advanced compiler construction. So we'll just focus that it is an ambiguous grammar which is of no use in any programming language, and it will generate more than one leftmost derivation tree for any one string. If you are getting a more than one leftmost derivation for any one string of the language, it is ambiguous grammar. And best example of that ambiguous grammar is if-else grammar. That is what we have seen today. So So this is sufficient for today. In next week, we'll start the new topic based on this, which is top-down parsing. Thank you all.